Hello, we're about to get started here. And I'd like to introduce Aditya, who will talk to us about merging similar functions in ThinLTO.
There are many applications which are sensitive to code size. They are larger applications, and most of the pieces of the program, they don't have a hot loop or something like that. So most of the compiler optimizations which are centered around performance are not very meaningful in that area. So I was looking into the code size optimizations. There are not many in LLVM. Also, there is, if you see the number of optimization passes, the amount of activity on the code size optimizations are not as much. Function merging is an optimization which is used to merge similar functions so that we can gain in the terms of code size. It is an interprocedural optimization, so it works on one translation unit at a time. In order to have the full power of function merging, we need to have this facility across the entire program. That will help reduce code size and will gain in those applications which are not very sensitive to performance. Okay. So this is the slide which kind of explains a very brief overview of how ThinLTO works. I just stole this slide from a presentation a few years back. Thank you, Teresa, for making this slide. I think this slide has been copied over and over in many places. This explains how ThinLTO works. ThinLTO is a lightweight version of link time optimization. It is mostly parallel. There is only a very thin layer of serial step. If we think in terms of the traditional compilation steps, the first stage is where the compiler takes C or C++ source code and parses it and a bitcode. There is only a little bit of addition here, that when the compiler knows that this is a ThinLTO stage, it also generates some kind of summary which can be used during the parallel link time optimization stage. The summary is added to the bitcode itself, and during the thin link layer stage, it is a serial step. So the compiler parses the summary from each module and populates to a giant module summary index. And that module summary index is globally available during the parallel code gen stage. This helps compiler take a very good advantage of the link time optimization, but at the same time, it does not suffer from the compilation time overhead compared to traditional link time optimizations. Function merging is a code size optimization. In LLVM, there is already a function merging pass, which can be used to merge identical functions. But I use the other version of function merging, which is in the open source, but it has not been merged to the LLVM trunk yet. It is useful for merging similar functions as well, and hence it can give much better code size gains. Especially for C and C++ based code base, where we have a lot of duplicate copies. For C++ standard library, if you take, for example, when we call those C++ standard library algorithms, for each type, they get instantiated in each translation unit. They are structurally identical in many cases. In some cases, they have very minor differences, like typecasting or something. They can be deduplicated into one and then gain in terms of code size. For example, this is a very simple example where we have two functions which are identical. They are in different translation units. Traditional compiler optimization will not, or function merging will not detect this. But when we perform link time optimization or ThinLTO, what will happen is there will be only one copy of function, and the two interfaces will just redirect to the one copy. We don't want to get rid of the interfaces because that will result in link time error. To port function merging to ThinLTO, it comprises of essentially 4 steps. The first step is to add hash code to function summary. So how the function merging works is it computes some kind of hash for each function, and that hash is a measure of some kind of structural and semantic properties of the function. And that can be used to compare one function to other. Instead of comparing the entire function, we just compare their hash code. And if the hash code of 2 functions are same, that means they have some similar properties and they can be merged, potentially merged later on. This helps discard a lot of functions which are obviously not similar. And then we have a bucket of similar functions, and then we can do expensive comparison, like instruction by instruction comparison there. So we save in terms of compile time in this case. The second step is to make merge function decisions. Once we find buckets of functions which are potentially mergeable, we have to decide that which of the functions can be merged actually. So we do a instruction by instruction comparison. It is a n-square algorithm, but on a much smaller n. And then we decide that which are obviously the candidates. And once we have those candidates, we keep them in the bucket and discard other ones which are not mergeable. The third step is to set up those similar functions to be imported. What this means is during the serial ThinLTO stage, we have to mark those functions that they can be imported, so that during the parallel code gen stage, they'll be moved from one module to the other one by the IR mover during the link time optimization. I'll talk about them in detail. And the last step is to run function merging as part of ThinLTO pass pipeline. So the first one is to add hash code to the function summary. What hashing means is to get some kind of measure of structural as well as some semantic properties, like number of basic blocks, or hashing the formal arguments of the function and the return type. Some of the semantic properties like calling convention, or like if function has var args, few things like that. The idea is to keep the hashing fragile. That way, we want to have a lot of matches, and then we can compare them instruction by instruction during in the second step. Once we compute the hash function, hash of a function, then we want to add that hash code to bitcode during the parallel, the first stage of the link time optimization, where bitcode has the function summary. So we have to change bitcode writer as well as reader, because later in the parallel code gen, bitcode reader will read the function summary. These are some of the pointers, like how to find the places where we want to add the function summary. Like these are bitcode indices there. The second step is to make merge function decisions. There are 2 important data structures here. The first one is a map of functions which are identical, and the hash code of that function. The second data structure is the list of functions which are the hosting functions. What does it mean by hosting function? When we want to merge a collection of functions into one, what we want to do is move the IR of all those similar functions into one module, such that during the parallel code gen stage, the compiler doesn't have to look into other threads. It can make decision separately just by having all the information available in one module. There can be a cost model to decide which function can be a hosting function. But for now, I just selected the first one. It can affect the performance actually, so as we will see later. The third step was to set up similar functions to be imported. The entire logic is in function import.cpp. It is a sequential interprocedural pass. It runs for each module. It works on the module summary index. So this time, at this point of time, we have not parsed the entire bitcode. That's why it is very cheap. But we want to be able to make the decision before the parallel code gen stage. The function import uses IR mover, which is a data structure, and it just works. You just have to mark which of the functions are needed to be imported, and that's about it. It works by moving the IR as well as the relevant declarations as well. So it's pretty modular in that sense. And the last step is to run the function merging optimization during the ThinLTO stage. So all we need to do here is add a couple of lines in the LLVM pass manager and schedule the function merging after the inliner, because inliner can undo the effects of function merging. That's about it. To have some kind of experimental measure to report here, I was looking for some of the open source projects, and then I started compiling using ThinLTO and realized it's not like so trivial. There are quirks there of build systems, of plugins, and they can come into your way. The first thing is, on the Linux-based system, we need to use Gold plugin. So we have to install a Gold plugin, LLVM Gold.shared object, and you have to have bin util somewhere. The other problem is the Gold plugin doesn't take like OS or OZ code size optimization flags for some reason. Function merging is a code size optimization, and using OS and OZ makes sense, but it was not possible. So what I did was I just used O3 for the results. The other parts are like the archiver and the ranlib. We need to use LLVM AR and LLVM ranlib. And then we have to deal with the quirks of the build system. Like for example, CMake is pretty simple to understand, but it adds link flags to the archiver. An archiver complains that I don't recognize FLTO equals thin flag, and it will just error out. So I had to add a wrapper LLVM AR.sh flag, which will just remove the FLTO equals thin flag and pass it to the remaining flags to the LLVM archiver. It might be helpful to change the build system as well, but depending on what the use case, you may resort to these kind of small tricks. This is the experimental result on OpenCV libraries. OpenCV is a library used for like computer vision. It has a lot of shared libraries, but I use the top 7 for this result. Except for one, we gain in code size for almost all of them, as high as 9%. The one where we lose code size is around like, it's pretty small, but still a loss in the code size. It may be because of the fact that I'm using O3, because during the O3 compilation stage, optimization flag, there might be inlining which is aggressive and like loop unrolling. Many other optimizations which are aggressive and quite oblivious to code size increase are enabled at O3. Okay, this is the part which requires a lot of effort, like tuning. We set up the optimization flag, everything works, and then you do experimental results, and sometimes we gain in terms of code size, but the performance can be too bad to be like tolerable. So we need to tune some of the flags. Function merging has some flags like how large functions you want to merge, or like what is the dissimilarity index. I did not write the function merging pass, thanks to people, Tobias especially. I just ported this to ThinLTO. The other issues with function merging across link time optimization is it will create cross-module dependencies. Let's say there are 2 modules which have functions which are identical, and they don't have any cross-module callbacks. Now what will happen is, after function merging, there is an edge, and there is a call from one module to the other. It can lead to page faults, and that can be harmful. So we can do, there's one alternative is to have some kind of profile guarded information to know which module is called first, and then make it as a hosting module, as we saw a few slides back. That can be useful. The other part is a lot of C++ standard library algorithms have forced inline attributes. So even if at OZ or OS compilation flag, they will get inlined. And those functions, if they were not inlined, they would appear as identical functions. But now they are in the middle of some giant function, and it is difficult to deduplicate them without having a complex algorithm. So these are the tuning that can be kept in the mind. And that's about it. These are the patches for review. I'm getting already so much reviews from Teresa. Thanks for feedback. I'll have to do a lot of work there. Questions?
All right, I have two questions for you. First one, why is it desirable to have another merge funcs than the one we already have instead of fixing the one we have? Like a lot of the stuff in the one you have is stuff merge funcs should do. So like it's easier to incrementally improve the existing merge funcs than to just land a big patch that's a fork of a prior version of merge funcs. Second question I have, it's kind of connected, is the main problem merge funcs has is it tends to diverge from IR. When new things are added to IR, it doesn't know about them. It's easy if it's a new type of IR node, but if it's a property in an existing IR node, we just don't know about it, which makes merge funcs merge things that are actually not the same and makes it diverge. Especially if you're trying to do fuzzy matching, it gets kind of tricky to do that properly with kind of merge funcs having its own view of what IR is and IR evolving its own merry way without merge funcs knowing about it. So how do you plan on fixing that?
Okay. Your second question dried my throat because I could not understand, but it was very complicated, I think. But I'll answer the first question first. The current merge function is strictly not as good as the merge similar function. There are two alternatives. What we can do is we can improve the current one. That will require a large number of porting and reviews. The other way is to just completely replace it and just remove the previous one. If it is strictly better and there are no reviews, that there are no regressions. So these are the two ways we can go about it. I guess based on what most people agree, I'll probably do either one of these. The second question was merge function is not makes some intelligent guesses about the IR, and it may be not possible to have a good matching there. I agree. I don't know. I don't have any good answer for that one for now.
Yeah, thanks, Aditya, for this work. It's really exciting to see people building on top of merge similar functions. What I was wondering about when you described all the flow there, what you do if merging actually fails. So it seems like you're making the decision
ahead of time, yes.
Yeah, ahead of time, what you're going to merge or what you could potentially merge, right? Because it has the same hash, and then you import those and so on. But what if it actually turns out that you can't merge them, right? Because they turn out to be not isomorphic, or because there are some instructions that are, that can't be merged.
Yeah, so that the body of the IR will remain in the new module now. Mm-hmm. That's about it. But from a correctness point of view, nothing bad will happen.
Oh, so you just move the function to
the IR. All the IRs we wanted to move during the ThinLTO stage, we make decision before ahead of time, right?
Yeah.
In the serial stage, so we mark those IRs to be moved, and they'll get moved. Mm-hmm. Yeah.
Okay. Yeah. So you might end up with functions being in a different place, but
I think so.
No other harm. Yeah. Okay.
Yeah.
Yeah. So related to that, so I noticed in your patch how you're doing the importing
Yeah.
part. So normally today when we do importing in ThinLTO for inlining, we import it as like an available externally copy, and you don't change really the source module you're coming from. But it sounds like here you're actually moving it. So you're actually importing it, and you have to, so what do you do? For the original location, do you mark it as like turning it into an available externally linkage, or how do you drop it?
Yeah, I have changed the linkage flag to available externally. If I remember correctly, I did that for I guess there is only one place which asks for the linkage flag, and I change it to available externally if it is in the module summary index.
Okay.
Yeah. So I think it will have one copy will get deleted, I guess. The linker will probably take care of it. I don't know.
Yeah, available externally will get dropped. So, okay, so that's a change. So you'll actually drop it from the original module.
Yes.
Are there any other hands? Okay, I think signed up. Oh, sorry.
What's the impact on debug information and debuggability for this function merging, if there's any?
Yeah, I think it will get spoiled. Yeah. Any compiler optimization has a great potential of spoiling the debug information. I'm sorry. Yeah. Okay. Yeah.
He's here, but he's made some improvements to the paths to handle debug.
Debug. Okay. Awesome. Okay.
Okay.
I was just wondering about the impact on compile time that this optimization adds.
I didn't include the compile time because when I measured the compile time, it was better, probably because I had a lot of similar functions in OpenCV, but it can go worse as well. It can go better in many cases where, because you have less functions to process in the first place, so less number of things to do in the parallel code gen. It can go worse because function merging does something. So yeah, it will depend on different kind of benchmark, I guess.
Just to answer the question on compile time, my former intern, maybe 4 or 5 years ago, did work on merge funcs for benchmarking on Chrome and Firefox and some of the big code bases, and improve compile time. If you do it early enough, you end up not touching like all the STL stuff and whatever else. You just dedupe a bunch of it. And then you do the fuzzy matching later. Then you spend more time trying to do fuzzy matching and reducing things, but you've spent less time optimizing things, as you were saying. So if you go back a few years ago and look at Jason's posting on merge funcs, you can see numbers back then for Chrome.
Awesome.
That's it.
Also, Facebook is hiring, so.
We get a thanks.